Okay, hearing none, let's get started with tonight. The plan for tonight, just so you guys kind of have a where we're going with this, where tonight is really going to kind of finalize and finish what I had hoped to lay down kind of a foundation for statics and reactions and free body diagrams and that sort of thing. And it really is towards the tail end of tonight that we hope to get to that we will actually start talking about the first topic of mechanics of materials, which is stress. So we're going to hit that tonight towards the latter part, but we're still going to finish up our review of statics and related things before that. The stress part it's actually kind of simple, so it really shouldn't take that long to do it, talking about the concept of stress. And then moving forward, starting on Tuesday, we're going to move to the next chapter, which is chapter 2, and start talking about strain. And then I think chapter 3 is where we start talking about the relationship between stress and strain. But that's getting a little bit further into the course. So if anybody does not have any questions about where we are so far, let's begin. Okay, so they're kind of picking up where we left off last Tuesday. We were talking about equilibrium in 2 dimensions, and rigid bodies have 3 degrees of freedom in 2 dimensions. So basically, up or down, left or right, and rotation are your 3 degrees of freedom. In 3 dimensions, of course, that jumps to 6 degrees of freedom. We have this symbol. This is actually a capital phi, but this is the symbol that I've seen used for degree of indeterminacy, or DOI. So I've seen it spelled out DOI. I've seen it use this symbol here. We're just going to use this symbol, but it's the degree of indeterminacy. The calculation for the degree of indeterminacy is R minus 3 plus C. That's your equation, where R is the number of independent reactions, and this is key, independent reactions on a rigid body. C is the number of special conditions. Special conditions usually would be a hinge, but there are other special conditions that we can have as well. Okay, so if your degree of indeterminacy is greater than 0, then that rigid body is both stable and statically indeterminate. If phi is equal to 0, then the body is both stable and statically determinate. And of course, if phi is less than 0, then the body is just flat out unstable. Having, well, again, going back to R is the number of independent reactions. So as we're going to see, we're going to walk through some of these. It's easy to get fooled. It's easy to get fooled by having a phi that's equal to 0 or something greater than 0, but the body is actually unstable. And that is possible because that some of these, what you think would be your reactions, are not independent. And I'll try to point those out as we go through. But if phi is less than 0, you're done. The body is in motion, it is not stable. Okay, so how do you determine stable, unstable, determinate, or indeterminate? And I guess stop here for a moment. If a body is stable, then it can either be determinate or indeterminate. But if a body is unstable, it is neither determinate nor indeterminate. It is just flat out unstable, okay? So determinate or indeterminate are 2 classes of being stable. Unstable is just unstable. Okay, so we start with our classic beam with the pin and roller. See this a lot. And so we count up our possible reactions. Remember last time we went through each possible source of support and looked at how many degrees of restraint are provided by each support. pins will give you 2, and a roller gives you 1. So we have degrees of indeterminacy, r minus 3 plus c. We have 3 restraints, 2 plus 1. We have minus 3 as a constant, and you have no special conditions. So 3 minus 3 is equal to 0. Therefore, this structure is stable and determinate. Okay, so what happens if I have 2 pins? It's even more stable, right? No. But it is, we have 2 restraints for this pin. We have 2 restraints for this pin. So phi is equal to r minus 3 plus c, which is 4 minus 3 is equal to 1. So in this case, the structure is stable and it is indeterminate to the first degree. What does this mean, by the way? What does this mean to you if you're trying to solve problems? If it is stable and determinate, that means one thing. If it is stable and indeterminate, that means something else. What's the difference?
Does it mean if it's indeterminate, that means you can't find the values of each support reaction using statics?
That's exactly right. Perfect answer. Yes. If it is determinate, that means you have 3 unknowns and you have 3 equations, so you can solve for your 3 unknowns. If it is indeterminate to the first degree, what that means is you have 4 unknowns and only 3 equations. So you can't solve for all of your reactions just using statics. You have to have more knowledge. You have to have something in order to create another equation in order to solve that type of problem. So yes, perfect answer. Determinate means you can solve for all your unknowns. Indeterminate means you're lacking some information in order to solve for all of your unknowns. Okay, next problem. I have a pin, I have a hinge, and I have a roller. A hinge really is just a pin, but it's like an internal pin. This is not attached to the outside world. So it's just terminology. It's really the same device, but a hinge is between 2 parts of the body, and a pin is supporting to the some support to the real world. So what do we have here? I have r equal to 2. I have a special condition. 1 degree of restraint has been released by this pin. What's been released is the moment capacity. In other words, it has no resistance to rotation at this hinge. It prevents it from going up or down. It prevents it from going left or right. But a hinge allows one body to rotate with respect to the other. So this is 2 degrees of restraint. This is actually 1 degree of freedom. It's been unrestrained by 1 degree. And we have 1 degree of restraint for this roller. So our degree of indeterminacy is 3 minus 3 plus the 1 for my special condition. That is equal to minus 1. Therefore, what do you know about this body?
It's unstable.
It is unstable. Correct. And this thing, if you look at it, yeah, it is unstable. Structure is unstable. Okay, next one. This one's a little trickier. I have a pin, I have a hinge, I have a pin. I have 2 restraints, I have 1 special condition, I have 2 restraints. So my degree of indeterminacy is 4 minus 3 plus 1 is equal to 0. Is this body stable and determinate, or is this body unstable? What do you think? Anybody? Would you jump up and down on it?
Unstable.
Okay, I got one vote for unstable. Anybody else?
Unstable.
But my equation says 0. How could it be unstable? Okay, so the answer is it is unstable. And the reason why it is unstable is that these two and these two are not independent. That's the problem. And the vertical component of these are independent, but the horizontal component of these pins is collinear. They're both in the same plane. And even though I kind of drew it this way, the hinge here is actually in the same plane as well. So if you're to sum moments at one end, you have two sources of restraint that are going through the same line. So they're not independent. And that is the problem. Even if this support was lowered so that this pin and this pin were not on the same plane, it still would not be stable because you could still draw a line right through all of your restraints. You could put a load on it and you have no resistance to that load. So this is unstable. Okay, next one. This is your classic cantilevered beam. I have 3 degrees of restraint at the end. Up and down, left and right, and the moment are all restrained at this end. So my degrees of indeterminacy, I have 3 minus 3. There's nothing special. So that equals 0. So this thing is stable and determinate. Okay, what about this dude? I got the cantilever beam, I got a hinge, and I got a roller over here. So I've got 3, I have 1 special condition, and I have 1 restraint over here. So I have 4 minus 3 plus 1 is equal to 0. And this is actually stable and determinate. Any questions so far?
Excuse me.
Mm-hmm.
So only in the first case, like we get the phi equals 0 and it's unstable, right? Just
This
in
one, this one here?
In the first case, the upper one.
Oh, this one? Okay, yeah, phi is equal to 0, but phi is not actually equal to 0.
So my question is only in this case, or there's other cases like we see like phi equals 0 and it's unstable?
Yes, there are an infinite different ways that you can invent a way that you have phi is equal to 0, but it actually is unstable. But the reason why there's nothing wrong with the equation. What was wrong with it is that this number right here is not actually 4. This number here is the number of independent reactions. And you only have 3 independent reactions, not 4. So that really should be a 3. And if you put a 3 there, this is minus 1. Does that make sense?
Yes, thank you.
Okay, no problem. But I did it the way that I did it because most of us, all of us, would look at this and go, oh, yeah, 2 plus 2, that's 4. Minus 3 plus, there's a hinge 1 equal to 0, and just move on with our lives and not realize that we missed something really important. So you have to watch out for anytime you have your reactions that are, usually it's collinear. Usually you have a problem where you have multiple reactions, but you could draw a line through all of them, in which case there's no resistance to the whole body rotating.
So the first case of number 1 would be indeterminate then?
This one?
Yeah,
No, it's unstable.
unstable, okay.
Yeah, so unstable is not determinate or indeterminate. It's just flat out unstable. And again, the reason that it is unstable is that, it's kind of hard to use this tool, but that 4 right there was the mistake. That's actually a 3. Not because I miscounted my reactions, but because that number R represents the number of independent reactions. Although I have 4 of them, not all 4 are independent in this case, only 3 of them are. So that's why this is actually -1.
Okay, thank you.
Okay. Okay, what about this guy here? This is what's known as a propped cantilever. So I have 3 restraints at the fixed end. I have 1 restraint at the propped end. So I have 4 minus 3 is equal to, 4 minus 3 is not equal to 0. Okay, found my first typo of the night. Slide 65 equals 1. Okay, so this is, I'm sorry, go ahead.
Somebody asked, how do you know if it's independent?
Oh, sorry, missed that. How do you know if it is independent? It really is by visual inspection. You really can't program anything to figure that out. It really is by visual inspection. And in fact, not to make anybody even more depressed or confused, but I plugged this one directly into my frame program. I have it's like RISA or RAM or ETABS. The one I use is called Multiframe. And I plugged this into Multiframe and it solved it. And it's unstable, but it solved it really weird. So in other words, the software didn't even pick up on that it wasn't stable. So you have to develop a skill of recognizing these things when they're unstable, because again, the idea is that you could draw a straight line right through all of your reactions. And if that is the case, then they're not independent. Does that make sense? Perhaps as we go through more of these, you'll see better what I'm trying to say. Okay, this is a typo, that's a 1. So this is stable and indeterminate to the first degree. What about this guy? Is that stable or unstable?
Unstable.
Yeah. This was kind of obvious, right? If that's a pen, this won't even hold itself up. By going through the equation, you have 3 reactions, you have a special condition. So 3 minus 4 is -1. -1 is less than 0. This is unstable. Clearly, this chunk out here would just flop over. Okay, what about this one? How many reactions do I have?
3.
I have 1, 2, 3. Each one of these is a roller, so each one of these only resists load in one direction. So I have 1, 2, 3. So my equation, I have 3 minus 3 is equal to 0, right? Is this structure stable or unstable?
Would it be unstable since all 3 reactions are pointing up?
Yes, it would. Yes, it is. This is actually one of my favorite ones. I call this the skateboard. It has no resistance to horizontal movement whatsoever. So this one is unstable. And again, what the problem is, well, in this case, you have too many reactions in one direction and not enough in the other direction. So this is not the case where you could draw a straight line through all of your reactions. Each one of these is in a different line. So that's not the problem. The problem is nothing is in the one coordinate direction. Okay, so you have to watch out for that as well. You have to have restraint in a horizontal restraint in the vertical, and restraint in a rotation. And so you have to just check that all of your reactions that you have cover horizontal, vertical, and rotation. See, back up to this one. I have 2 in the vertical, I have 1 horizontal, and I have 1 moment resistance. So it is stable, and the 2 make it indeterminate. So does that make sense, everybody?
Yeah.
Okay, so the skateboard is clearly unstable. That's why we have to wear helmets. Okay, so I'm going to work through an example. This one's a little bit more involved. It's going to take a little time to go through this example. But here is an example of a simply supported beam. I have a pin at one end, a roller at the other, and I have 2 different types of loading on here. And what I want is all 3 of my reactions. I have a horizontal and vertical, and I have a vertical. And I want internal loading at B, C, and D. That's what we're looking for, okay?
Professor, just to clarify, is the load on the left 3 kips per foot?
Yes, it is.
Okay, thank you. It's a
Yeah. Yeah, sorry, this one came out a little small. But yes, this is 3 kips per lineal foot. This is A, B, C, D, E, 10 kips here, 4 feet, 5 feet, 6 feet, 3 feet, and 6, 6, 6. You can always, this is available on Blackboard, so you can zoom it up on your version, and hopefully all this will read. Okay, so for my solution, first step is I need to draw a free body diagram for the whole body to find my reactions. So a free body diagram is not the same thing as my design sketch. The free body diagram, if I have any linear loads on here, I have to convert them to a vector, a force. So 3 kips per lineal foot times 6 feet is 18 kips. All of my reactions become unknown forces, and I label them as such. So I have a reaction at A in the X direction, a reaction at A in the Y direction, a reaction at E in the Y direction. Then we sum our forces to find our unknown reactions. Some moments about A, I have 18 kips times 3 feet. I have my unknown reaction at C times 18 feet, and I have my 10 kips times 12 feet. All of that equals 0. And I solve for my reaction. Why did that say C? There's another typo. Sorry guys, but I'm going to write these down so that they don't just keep propagating. And my reaction at E is 9.67 kips up. Sum the forces in the Y. My reaction at A, Y, minus 18 kips, minus 10 kips, plus my reaction at E equals 0. Reaction at A is 18.33 kips up. Do not forget this part. This is really easy to overlook. There are no horizontal loads on this beam, but I still have a horizontal reaction. So I sum the forces in the X direction, and my reaction at A in the X direction is equal to 0. It may seem trivial, but this is a pretty exact class and a rigorous class. Don't forget, if I ask for all reactions, to give me the one that's in the X direction as well, even if there are no loads in the X direction. Okay, so we have our reactions now, all 3 of them. Let's find our loading at B. So this is my design sketch of what's happening from A to B. I still have this linear load that's going from A to B, but remember the linear load was 6 feet long. I'm not going to include all 6 feet because 2 feet of it is on the other side. So I don't care about that. That goes on the other side. So all I have is my reaction at A and my linear load from A to B. So now I translate this to a free body diagram. I have my reaction at A, I just found to be 18.33 kips. I have 3 times 4 is 12 kips. And that's in the middle of this load, so that's 2 feet from the end. Okay, so this is probably where most students get hung up. If you're going to get hung up, if you're going to have a problem, this is where most likely the problem will be. And that is they already found this to be 18 kips, so they keep using 18 kips, even though the cut is somewhere in between the end of the linear load. So if we all agree that this is my free body diagram, I have a shear, I have a moment, then I can sum my moments about point B. I have 18.33 times 4 feet minus 12 times 2 feet minus counterclockwise, so minus my moment at B. My moment at B is 49.32 kip feet, positive. Sum the forces in the Y. I have minus VB plus 18 minus 12 equal to 0. So VB is 6.33 kips, also positive. Okay, any questions on internal loadings at B? Again, internal loads do not have direction indicators. They are only positive or negative. Okay, find the loading at C. So if I draw a sketch from A to C, my design sketch from A to C, okay, now I have my end reaction and I have the full length of my linear load because I'm now beyond that. So if I draw the free body diagram, I have my 18.33 kips at the end. I have my full 18 kips at 6 feet, which is 3 plus half of 6 is 3, so 6 feet. And I put my unknown VC and MC. Some moments about C, I have 18.33 times 9 feet minus 18 times 6 feet minus MC counterclockwise. So MC is 56.97 kip feet, positive. Some forces in the Y direction. I have minus VC plus 18.33 minus 18, all equals 0. VC is only 0.33 kips, but positive. Okay, everybody tracking? Any questions?
I have a question.
Mm-hmm.
Oh, they just asked it in the chat, but I'll just say it. How come you don't put at the internal loadings? Why are there not like normal forces? Is it because it's 0 in this case?
It is. Yes, it is. Yeah, no, that's a great question. That's a very good question.
So like on homework, if it's 0, you wouldn't want us to like even state it in general?
No, you can state it.
Okay.
You can state it. It was somewhat that I was trying to keep this as clean as possible, and that's kind of a lazy answer. But I was trying to keep this as clean as possible. But you're absolutely right. You have an unknown normal force in here as well, and if you have any homework problems or what that has a beam. Some of them have like an elbow in them, like this. And so I'm glad you asked that question because the normal force is not always equal to 0. You could have a beam that looks like that, and you could have a pin, and you could have a roller. Well, can't draw a roller that way. Let's try that way. There you go. Okay, and you could have some load on it like that. So even though all your loads are vertical, because of this kink in the beam, you're going to have some normal forces in this section of the beam. You'd have some normal forces in this section of the beam as well. So That's a great question. This beam was simply supported, and the reaction at A in the horizontal was equal to 0. So I neglected to solve for n in all cases because n is trivial. It's equal to 0. But just recognize that if you had something like this, n will not be equal to 0, and you'll have to solve for it. Did that answer your question?
Yeah, perfect. Thank you very much.
Okay, thank you.
Excuse me, Professor.
Yeah.
Okay, so for like you assume that the shear force at C is like to the down, like it's going down, right?
Yes.
Then you got it positive, so it's like going down, real. Because if you get it like if you do it negative, so it means like it's up.
Yes. Okay.
Like I mean, we always we have to assume it. For example, if I want to solve a question, I assume it's like to up. Then if I get it positive, it's like my assumption would be right.
Okay. So the thing is, this is later on in the course. Oops, I didn't want that. Later on in the course, we're going to be doing shear and moment diagrams. That's a big part of this class is shear and moment diagrams. And shear and moment diagrams, see what we're doing here is we're just doing a spotlight. We're just looking at for the shear and the moment at one point. And then we go through all this again to get the shear and moment at another point. That's not very convenient. Later on, we're going to learn techniques so that you can get the shear and moment at all points with a shear and moment diagram. But when we do the shear and moment diagrams, what we're going to learn is that we have to have a consistent sign convention. And again, this is jumping ahead to like weeks, like I forget how many, 6 or 7 weeks ahead. But we're going to have a constant and consistent sign convention. And what that's going to say is that when you're doing a free body diagram of the left-hand piece, positive shear is down, and positive moment is counterclockwise. But when we do the shear and moment on the right-hand piece, positive shear is up, and positive moment is clockwise. They're equal and opposite. And so hopefully I'm answering your question. It doesn't really matter at this point in the game because we're really just practicing how to solve for internal loads and moments. We're just summing moments and learning how to do free body diagrams and cuts and things like that. But it is going to become very important later on because a positive moment is very different than a negative moment. A positive moment will put a beam in compression at the top and in tension at the bottom. And just for example, a concrete beam, you have to put your rebar where the tension is. So if you think you have positive bending and you actually have negative bending, you're going to have a huge problem because all the rebar is going to be on the wrong side of the beam. So positive bending and negative bending are very important to distinguish. And you can only get positive and negative right if you use this sign convention. So I'm just kind of alluding forward to what we're going to be doing by putting the positive sign convention as it's supposed to be, but we haven't really talked about it yet, and we're not going to for several weeks. Did that help?
Yes, thank you, Professor.
Okay. Okay, we have one more point, point D. So we do our design sketch of the beam from A to D now. So basically we're just making cuts. We're just cutting it and we're looking at what's on the left-hand side. But what has happened now that we've gone from C to D is we have this load is now included in our free body diagram. So we take this and we draw our free body diagram, right? Kind of pick it up on a pattern. It's a very repetitive system here. And each time we do a new cut, your eccentricities, your moment arms are getting bigger, right? So we have our 18 from the linear load. We have our 10 from the point load. We have an unknown VD and MD, and we have our known reaction at A. So summing moments about D, I have 18.33 times 15 feet, minus 18 times 12 feet, minus 10 times 3 feet, minus my unknown MD equals 0. My moment is 28.95 kip feet at this point. And sum the forces in the Y. I have minus VD plus 18.33 minus 18 minus 10 equals 0. So my shear at D is minus 9.67 kips. And so again, we just kind of did spot checking. We looked at the internal load at B, at C, at D, and you see how much work it was for each one of those. So later on, we're going to develop techniques to find diagrams that illustrate the shear and the moment at every point on the beam, not just discrete points that you're looking for. Okay, any questions on that? Okay. Thus ends our review of statics. Hopefully it was helpful. Hopefully as we move further down into this course, it will continue to be helpful. I have noticed in the past that going into new topics, some of the older topics from statics kind of comes back to bite people. It becomes a hindrance. So in other words, later on down the line, I may have an exam question that's asking about shear and moment at such and such point. Or we may be getting even more advanced than that. We may be looking for stresses or strains or deflections of a beam at such and such point. And if the student were to not be able to come up with the right reactions, which of course is the very first step, then everything from that point down is going to be wrong. If you haven't even solved for the right reactions at A and E, like in this problem, then you could see that every single point from that point down would be incorrect because of that initial assumption or mistake. So that's why I wanted to spend 2.5, nearly 3 lectures just going over some of these topics from statics before we got to this, stress. This is actually the first topic of mechanics of materials. Okay, so last chance. Any questions before we jump into mechanics of materials? Okay. All right, so what is stress? Other than it's midnight and you have a final exam the next day and you haven't finished your homework. Not that kind of stress. What is engineering stress? Engineering stress is really simple. It's defined as a force divided by an area. That's all it is. So, and better yet, there are only 2 types of stress: normal and shear. Normal stress or shear stress. So starting with normal stress. Normal stress in mechanics of materials is generally designated with sigma. And it may have subscripts to further define what sigma is, but generally speaking, if you see a sigma, you are looking at a normal stress. So here is a normal stress. I have some kind of an element. I have applied a load of N to this element. And if I take n and divide it by the surface area of this surface, then this is your sigma stress. And as you can see, the sigma stress and the original force causing that stress are normal to this surface. This stress here is normal to this surface. Okay, so sigma is equal to n divided by A, where A is the area of this surface. For example, super simple, n is 123 kips. A is 1.27 inches squared, which just happens to be the area of a number 10 rebar. So if I take sigma is equal to force over area, then I have 123 divided by 1.27 inches squared. Therefore, we have 96.85 KSI, or the normal stress. The other type of stress is shear stress. Generally is designated by tau, or the little kinky T there. And shear stress is just like it sounds. If you put a shearing load on a member, then if you take that load over the surface area, then the shearing stress is the load divided by the area. But the shearing stress is parallel to the plane as opposed to perpendicular to the plane. Shearing stress is equal to the shearing force divided by area. Back one too far. So what happens if you have a force at any other angle? It's not 90 degrees and it's not parallel. Say you had a force that was 45 degrees to this plane. What does that mean?
Would that mean there would just be horizontal and vertical components of stress?
That's exactly right.
Or like normal and shear stress?
Yes, that's exactly right. So if you had a force at any other angle other than parallel or perpendicular, then it would cause a stress. It would cause a stress at that same angle, but that stress could be resolved into the normal stress and the shear stress. So you would have one component of some kind of a skewed stress. One component would be normal, the other component would be shear. So a force or stress at any angle can always be resolved to a normal force and a shear force, or a normal stress and a shear stress. Okay, nomenclature. We got to get our hands around what do we call these things. So if you have a coordinate system, and this is just kind of arbitrary, but I got a y, x, and z axis on this thing. So if I have a normal stress in the z direction, then that is going to be sigma sub z, or sigma z. And the z indicates on a normal stress that the normal is in the z direction, like so. So this would be sigma z, parallel to the z direction. And likewise, sigma x would be in the x direction, sigma y be in the y direction, as so. So this is your three directions. Of course, the other three sides would just be minus sigma y, minus sigma x, minus sigma z. So we don't really need to reiterate all six faces. The three are sufficient. Now, if you have a shearing stress, that's a little different. So if I have a tau zx, then that represents a shear stress because it's tau on the z plane in the x direction, like so. So this surface here is it's perpendicular to the z direction, or it's normal to the z direction. So the first z is telling you is that the shear stress is on this plane, normal to z. And then the x is telling you which direction it's going. It could either be x or y. and this one's going in the x direction. Likewise, you can have zy, which would be going in the y direction. Okay, so again, these two subscripts, the first one is the direction of the surface normal to the plane of shear, and the second is the direction of the shear stress itself. And here's all three faces that are visible to us. So on the z plane, I've got tau zx, tau zy. One's going in the x direction, one's going in the y direction. On the y plane, I have tau yx, tau yz. On the x plane, tau xz, tau xy. So that's how that works. And again, if you had a shear direction in some other direction other than the coordinate axes, then it could always be broken down into the resultant components along the x and y directions. Okay, any questions? Okay, so we have some units associated with shear. Stress, I'm sorry, units associated with stress. Stress, whether it be normal or shear, is force over area. So the units of force over area would be pounds per square inch, PSI, or you could have kips per square inch, which is KSI. These are probably the two most common. Or in the SI system, you can have newtons per square meter, which is a Pascal, or capital PA for pascals. Particularly in the SI system, you don't want to write out how many pascals things are because the numbers get really, really big. A newton is not a whole lot. I forget what it was in terms of pounds. Like 1 newton is 2 pounds or half a pound or something like that, but it's not a whole lot. So imagine if it's 1 pound, imagine 1 pound over a square meter. That's not a lot of pressure. That's very, very little pressure. So that means that 1 Pascal is not a whole lot at all. So that's why we invented kilopascals, which is 1,000 pascals or 1,000 newtons per meter squared. We have megapascals. Now we're getting somewhere. A megapascal is 1,000,000 pascals or 10 to the 6 newtons per meter squared. Megapascals, these kind of come into the strength of concrete. I think, gosh, if I remember right, like concrete is on the order of 40 megapascals in strength. And steel is in the 300 to 500 megapascal range, somewhere in that range there. So these become much more useful, megapascals. And we have gigapascals, 1 billion pascals, or 10 to the 9 newtons per meter squared. And you might be thinking to yourself, where on earth am I ever going to see a gigapascal? Well, right here in this course, because we're going to talk about a quantity known as Young's modulus of elasticity. And in the customary system for steel, Young's modulus of elasticity is about 29,000 KSI, which translates to about 200 gigapascals. So these are relevant. Again, I mentioned this, I know, a couple lectures ago. My recommendation is when you are doing problems in the SI system, convert, like right from the very beginning, convert everything to newtons and meters squared. And then just keep track of all these multiples, 10 to the 9th, 10 to the 18th, whatever it may be, but keep your units straight. Actually, the same goes in the customary system as well. Choose pounds or kips, whichever is more appropriate. But if some parts of the problem are in feet and other parts of the problem are in inches, you're going to want to convert everything over to one or the other, and usually inches is what you'll be using. Any question at all about this?
Professor, so if there's an object with stress being acted on it, does it have both normal and shear, or does it have one or the other?
It can have both, and it can have one or the other. All three are possible.
Is it just depending on the system?
Yes, yes. I'll draw you an example. Okay, so let's say you have a support and you have a steel rod hanging from that support, okay? And then hanging from the end of that steel rod, you have some mass, some kind of weight. So this particular rod, if you find for your reactions, what you're going to find is that this rod is in tension, and that's it. There's nothing else on it. There's no bending moments on it. There's no shear on it. It's just pure tension. So this would be one case where if I cut it open right here and I looked at, oops, well, anyway, I looked at that. What you would find is that you have a normal stress in this rod equal to this force divided by the area of the rod. So that would be all you have is just normal stress. Okay, so far so good?
Yeah.
Okay, so then can I invent something that has this would be pretty close. So you have something short and stocky, and you put a shearing load on it, and you have a shearing reaction on that. It's not truly 100% shear because there's some eccentricity between these two, but it's as close as you can get. And so if you were to slice this open lengthwise and look at the stress, it's almost 100% shearing stress. There's no normal stress on it because you don't have any component of load going in the normal direction. So this would be pure shear. The other one was pure normal. And then of course you can have any, an infinite number of ways to get something in between. Like if I draw something more like that, and if I was to put a load on it that looks like that, then I most definitely would have some shear and some normal stress on that.
Okay, thank you.
Okay. Any other questions? Okay. The next topic that we have is something called factor of safety. And I bring this up now because I think it's going to be in your homework too. At least as a topic, it might be coming up in your homework too. So this is factor of safety. This used to be the way that we designed most everything. And I'll get to kind of how we design a lot of things today is not with the factor of safety, but originally factor of safety was really kind of the way we designed most things. And well, let me tell you what it is, and then I'll tell you how we designed to it. So it's abbreviated FS, factor of safety, and it's equal to sigma fail over sigma allowable. Or it could be tau fail over tau allowable as well. It really just means the failing stress over the stress that you are going to allow. Okay, so let me define this. Failing stress is the stress at which experimentally or theoretically derived capacity. So the failing stress should be the stress that whatever it is you're designing fails. If it's that tension rod I just mentioned a moment ago, then it might be the yielding stress of that steel is your capacity is based on the yielding stress. If it is a block of concrete, then the sigma fail could be the stress at which that concrete block crushes. There is a stress where you're loading it, and all of a sudden that block just crushes and fails dramatically. That would be your sigma fail. So whether or not you derive this experimentally or you have equations to derive what that is, this is the stress at which you would expect the material to fail. As opposed to sigma allowable or allow, this is the stress at the actual design load. This is what you are allowing into your material. Okay, is that clear for everybody? So for example, hopefully maybe this example will help you. I have a steel rod and I'm applying 12,000 pounds to it, or 12 kips. What is my factor of safety? The rod is a 1-inch diameter A36 steel. So that is the size and material of this rod. What is the factor of safety with the given loading? So I have the size of the rod, I have the material of the rod, and I have a load of 12 kips. Solution. Okay, so I need to find the area of steel. The area is pi r squared, which is 0.785 inches squared. So sigma allowable is the load that I'm allowing onto this rod. So that is, all stress is force over area. Stress is always a force over area. So N over AS is equal to 12 kips over my area of steel, 0.785 inches squared. Kips over an inch squared, of course, is KSI. So 12 divided by 0.785 is 15.29 KSI. So again, the terminology may be a little backwards, but basically this is saying I'm allowing 15.29 KSI on this steel rod. Now we need to find what is its fail. Well, I know that A36 steel is going to yield at 36 KSI. And you would know that too from looking at the back cover. Okay, so I don't know if you guys can see me on the camera or not. I think in the video maybe you will, but all I'm doing is opening up to the back cover of the textbook. And I'm looking under US customary units. And I am flipping down about halfway down that table is steel alloys. And of the 4 steel alloys that are listed, structural A36 is listed as the first one. So then I move over towards the right here, and I see the category, the column of yield strength. And the yield strength for A36 steel is coincidentally 36 KSI. Okay, so if you review this and you can see this, I'm finding it from the table. So in many ways, we consider, and I know some of these terms I haven't covered yet. We're going to talk about them a lot more in a couple of lectures. But in most cases, a ductile material, the stress that causes a ductile material to yield is basically what we designed. That's its failing stress. So we're going to consider the yielding stress of this ductile rod, 36 KSI, as my failing stress. So my factor of safety then is my failing stress over my allowable stress, 36 over 15.29. I get a factor of safety of 2.35. If the factor of safety was less than 1, well, then that means that the material is going to fail prior to reaching my desired load. So that's no good. You can't have a factor of safety less than 1. The minimum factor of safety is usually about 1.5 to 3, sometimes more, sometimes less. But this is how you derive a factor of safety. Now, as I mentioned, originally in design courses, this was the way we designed things. So, for instance, for steel, what they would do in steel is you add up your loads as best as you can, and then you compare them to some failing load, and you get a factor of safety. And then the codes would basically say what the minimum factors of safety needed to be. And they would differ depending upon what you're doing. So a rod in tension, maybe this would be 1.6. A beam in bending, maybe this would be 2, something like that. But this is how we used to design a lot of our materials. We still do some materials this way, but most materials now are based on capacity-based design. And what is the difference? Capacity-based or strength-based or LRFD-based, you'll hear these terms, design looks at a reduced ultimate capacity compared to a factored load effect. So we have reduction factors, phi or phi, are less than 1 to account for material weaknesses or workmanship issues. Load factors are greater than 1 and account for uncertainties in the assumed loading. And you have different load factors for different types of loading. Dead load is pretty accurately assessed, so the load factor is 1.2. Live loads are not very accurately assessed, so that's a load factor of 1.6, for example. Okay, so we can do our same example, but now we're using capacity-based design. The rod is the same rod. Is the steel rod acceptable with our capacity-based design? Phi, and I know I'm just pulling these out of a class you haven't had yet, but when you get to these classes, you'll find that phi is 0.9 for axially loaded members. The area of the steel rod is 0.785, like we found before. The yield is 36, like we found before. So this P sub n is the nominal capacity of the rod, is the area times this allowable stress. So we're, again, kind of working it backwards. Stress is equal to force over area. Well, the capacity is equal to area times stress. So 0.785 times 36 KSI gives me 28.26 kips. That is the theoretical load it takes to yield that rod. Then my allowable capacity is phi times that, 0.9 times 28.26, 25.4 kips. And my load on this gets factored up. See, 1.6 times 12 is 19.2. And my VPN, my allowable capacity, 25.4, is greater than 19.2. Therefore, my design is adequate. This is just a little taste of strength-based or capacity-based design that you'll see later on. Allowable stress design, factor of safety, is the older design method, but many materials use capacity-based design in modern codes, including steel, concrete, masonry, and wood. Several materials, including steel, masonry, and wood, still allow allowable stress design because some people like it and they just won't give it up. And one material, soil, is still exclusively allowable stress design based. Any questions about that factor of safety?
What was P sub U again?
P sub U, in the world of capacity-based design, anything that has an N on it is a nominal capacity. Anything that has a little u on it, that is the ultimate load. And that's how it works. So PU is the ultimate axial load. VU would be an ultimate shearing load. MU would be an ultimate moment, so on and so forth.
Okay, thank you.
Okay. Any other questions on the factor of safety? Okay. Shearing stress. And this is kind of a little subtopic of stress in general, but this is talking about shearing stress. And we can have single shear where you have, say here, 2 plates and maybe they're glued or welded together. This is what's known as single shear, because if it was to shear, when the material fails in shear, there's only one shear plane, as you can see. So this would be the failure plane, and it only has to shear across one plane. For a bolted connection, you might have something bolted to a larger piece. And if this was to shear, it shears through the bolt in one place. One failure plane through the bolt. So this is still single shear. Not to confuse that you have 2 surfaces here because it failed. Don't confuse that. It's just one plane that it fails through. And tau, remember tau is the shearing stress, is equal to P, the load, over the area of the bolt. So you just have one area of the bolt. Or you could have double shear. Double shear is where you're bringing the load through 2 plates. So the full load is in this plate, but each one of these plates by statics is sharing half of the load. So when this fails, as you can see, it has to tear through 2 planes. So if the material fails in shear, there are 2 shear planes. So you have the failure plane here and a failure plane here. So this is known as double shear. For a bolted connection, same idea. You may have one single bolt. This is the same bolt, right? This is one hole and you dropped in one bolt and threaded on a nut. You have one bolt, but when it fails through that same bolt twice. So this is known as double shear. You have 2 failure planes, and tau is equal to the total load P divided by twice the area of the bolt. So this is the end, but this is a very important concept about single shear and double shear. And of course, you could add more plates to this and have triple shear and quadruple shear, but this is the most common. So what is the danger of not really getting this? What is the danger of not understanding between single shear and double shear? Well, the most obvious danger is if this bolt was sized to be in double shear, and then someone down the line changes that detail and changes it to single shear. Well, you just doubled the shearing stress on the bolt. If it was designed to have 2 failure planes and you reconfigure it to only have one failure plane, you have now doubled the stress on that bolt and you may have a failure. So it's very important to understand the differences between single shear and double shear. Okay, we are nearing the end. Does anybody have any further questions or anything that perhaps I didn't touch upon that you saw that you might need for your homework for next Tuesday? I made it up. Again, I'm sorry. The question was PU equals 1.6 times 12 equals 19.2 kips. Where did you get the 1.6? And there's a very definite answer to that. It's just that you haven't been exposed to this yet. It comes from your design courses. So your steel design course, your concrete design course, those types of courses, ultimately comes from a code book called ASCE 7. And the current year that we're working on now is ASCE 7 year 16. And that's where in chapter 2 of ASCE 7, all the load factors come from. And there's a lot more. But just for example, dead load could be 1.2, live load is 1.6, soil load is 1.6, seismic loads, coincidentally, is just 1.0, and wind load now is just 1.0. But that's because in the seismic chapter, they've already made the seismic load a big load. And in the wind chapters, they made the wind a big load. So their load combinations are 1.0 each. There's icing loads, there's stressing loads from creep and shrinkage, there's truck loads, impact loads, rain load, ponding load, there's even a tsunami load. We're getting pretty obscure, but there's a load factor for each one of those. And anyway, to answer your question, it came from ASCE 7, and you probably will not hear or see that again until your design courses. Any other questions?
Professor, do you mind just going back to the single shear slide for a second?
Sure.
Thank you very much.
That one there, or did you want the unbroken?
No, this one's good. Thank you.
Okay. 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 Next time, we're gonna. Is there a Discord group for this class? Not even sure what that is. Forgive me, I'm old-fashioned. Anybody else can answer that for Natalie? Or other students? Okay, no problem. So while other people are perhaps answering that, just a look ahead. Stress is chapter 2, and then we're going to be moving in next class, we're going to be moving to chapter 3. Oh, I'm sorry. No, pardon me. Chapter 1 is stress. Chapter 2 is strain. So please have read through chapter 1, at least over the weekend. And you should be reading in chapter 2 when we meet again on Tuesday. Okay, so I will now conclude this lecture. Thank you, everybody, and have a great weekend.
Thank
Thanks,
you.
Professor.
Bye, Professor.
Thank you.